Hi everyone, we'll be getting started in about 1 minute time. So thanks everybody for joining so promptly. We'll give it another 1 minute until we get started. Thank you. Okay, I think it's 5 p.m. on the dot, and I think because this is a fairly longer session, we'll just get started if that's okay with AKR trainer. If he just gives me a nod, we'll just get started. People are joining the call, and it's racking up. We're nearly at about 250 at the moment and counting. So I guess I'll just start off by introducing myself. My name's Sarah. I work at Sparkline as HR and education director. So part of my role is to involve in training programs and training partnerships such as Sparkline's partnership with Shopee to join you today and run our second workshop of Shopee Code League 2021. We did one last week, which was Intro to Data Science. So hopefully some people came to that session and really enjoyed that one and felt like the spark, no pun intended, had been ignited and you wanted to come to the second one today. So we're really pleased to have you all here. So very, very warm welcome from us all at Sparkline. I'll just be doing a very brief introduction. Don't worry, I'll be passing you over to the man himself, AK, your trainer for today very soon. So who is Sparkline? And if anyone was with us last week, we like to just give a bit of an introduction to who we are for newer people that are joining us, just so you can kind of keep a reference to who you're actually receiving your training from, and you can kind of make note of that as you will. Also, just to know who we are, to please feel very, very free to connect with us after the session. We have a Sparkline company page on LinkedIn, a Facebook page. We also have a jobs page that we keep up to date on both websites and our Wantedly, which is a social hiring platform that you might have heard of. So there's lots of ways in which to connect with us and we'd love to be in touch. We're a digital analytics consultancy. So it's pretty niche in terms of the area that we focus on as a business. We focus on the web analytics field. We work with clients to run various consultancy projects. We train with clients and individuals and enterprise organizations, government agencies. And AK and his team, they're part of the business as well, looking at product development, data automation, tool building, which is where a lot of that machine learning model building will come into play for a business, just for context. So that's really where you'll gain a lot of your learning in that kind of area today. So we've been established for about 8 years in business, in market here in Singapore, and we work all across the APAC region. Just some of the clients that we work with, and maybe just a kind of snapshot for you guys in terms of the type of learning that you're going to be exposed to through Shopee Code League 2021 and through some of these workshops. These are the types of clients that we as an analytics consultancy work with on a day-to-day basis. And these are the types of organizations that are accelerating their digitization, their appetite for data, their appetite for digital transformation and machine learning, and incorporating this type of technology and this type of tech acceleration into their business right now. So kind of good for that context setting to think about the skills that you're building and the career that you might be forging into, and what type of brands, what type of industries is looking for this type of talent at the moment. I mean, there's a plethora, but these are the types of brands that we work with on a daily basis. And then finally, just as part of our business line, obviously being that training and education focus. We work with individuals and enterprise, and we run analytics workshops. So today, just be a little bit of a taster of what that is like. So do contact us if that's something that you'd like to follow up with in the future as well. And for all you individual learners, it might be a bit more relevant that we do have an online e-learning program. Mildred and the Shopee team will be sending out some details of how Shopee Code Leaguers can access this learning at a discount price for joining the session today, and also just to get that kind of further introduction into the world of digital analytics. And as a business, if you do come and connect with us and maybe work with us one day, you'll be helping to form those enterprise solutions, which are often very customized for clients to help with their upskilling in-house. So just a bit of a snapshot and a bit of context setting for who's training you today as a business. And this is the offer that we'll be sending out. So the links there, we'll copy and paste that and add that into the chat later. You'll also have all the details that will be sent around, including a cheat sheet, some follow-up information that AK, our trainer, will be putting together for us. We don't record these sessions or send around the slides after the session, but we will be sending around a follow-up, access to some of our learning and a bit of a summary of some of the learning that you've touched upon today. And then finally, that just leaves me to introduce your trainer, who's going to take you through the meat of today's session, AK. So he's our lead solutions architect, our head of the delivery team at Sparkline. He really works with all of our clients and our delivery team to ensure that the technical brief for everything that we do is hit and on the mark every time. He does a lot of training with our clients. He runs a lot of our government partner training programs with IMDA, with NTUC, TTAB across Singapore. Previously with, you might have heard of a company called Facebook. AK spent quite a few years working with those guys. And he's very deep into the data analytics, machine learning, the technical architecture in the data space. So you've got a great person here. You're in really good hands today for your session. We're really excited to hear what he has in store for us. So thanks, guys. Very, very warm welcome again. Please do connect with us and myself on all those platforms I mentioned. Contact us for any further learning opportunities. And finally, just really enjoy today and very best of luck with the rest of Code League 2021. Over to you, AK.
Thanks so much, Sarah. Welcome, everybody. First, to our second module of the Shopee Code League. This is going to be a course oriented towards beginners. So it's machine learning models or statistical learning 101. In this course, we aim to serve or build intuition for anyone who is just beginning, getting started and is curious, to even seasoned professionals who may have been doing this in their sleep over a long period of time, but now want to come back and challenge the fundamentals and look at it from a different perspective. So I saw a few questions on the chat already about who is this talk geared towards. The answer is it's mixed towards everybody. We will try to build intuition up from first principles while also dealing a little bit with code. And don't worry, you don't have to have any prerequisites for this apart from a sense of curiosity. A little bit of intelligence in just being able to parse some formulae in the initial bits, but we'll also try to keep it high level and we'll keep it conceptual where you can understand what the math is trying to do rather than get into the weeds of exactly the formula itself, even though we'll try to do that in the first module a little bit. Now, we will be using Google Colab heavily for this because it's a pre-installed environment that has all of the hotness in it. But you don't need to use it if you don't, if you're not comfortable with it right now. We'll be sharing a link with you that you can take and you can use later on. So with that, we'll just quickly hop in and get started. For those who have attended the first module of the session, this might already be a little familiar to you. But it's important to build up complexity from the simple layers that you see over here. So please bear with us for the first few slides as we go once again, for those who are revisiting us from the first session through linear models and linear regression, so to speak, and building intuition in from there. So without further ado, let's just hop right in. Now, for those who have been here in the past, in our previous session, this might be familiar to you. But let's assume you're buying a house in Singapore. It's the emphasis on buying because this is a very expensive market, right? And the reason we pick on the Singapore market is not because we are picking on the Singapore market, it's because it's heavily land constrained, which means people don't build wide, they build up, and spaces are a premium. So imagine you want to simplify a question that all of us might have, which is what is the cost or the price of a given house somewhere? You might talk to one of your real estate friends, and you might notice that given a sense of a location, like let's say Newton, Novena, Woodlands, wherever, and given a sense of the number of bedrooms, many people in Singapore might be able to narrow down the price of a house to a high degree of certainty. That's because we notice as human beings that we're really good in intuitively understanding patterns within large clumps of unordered sets of information. And that information is data in its own right? So if you spend some time digging through propertyguru.com or gone through real estate directories and looked at house listings anywhere, you might start building up a fair degree of expertise yourself in terms of what a house might cost given a set of attributes. But in this case, what we'll do is we'll imagine that we've gone around the Singapore market and we've taken all of the houses that we've seen over there, and simplistically, we'll just be throwing all of them onto this two-dimensional grid over here. For anyone who's gone through high school geometry, this should be very familiar to you. It's simply a X and Y plot that we're dividing up into the classic MBA 4-quadrant plot, right? So you have on the X-axis, which is the horizontal axis at the bottom, you have square footage. So this is the size of the house, starting from low, which is like 0 square footage, all the way to like really high square footage. You have price on the Y-axis going from low to high as well, where you have low price houses at the bottom and you have high price houses at the top. This splitting this entire grid, the familiar XY grid, into 4 quadrants simply by drawing a line down the middle and a line across the middle, as you see over here. Now, what you'll notice is this splits this grid into unequal 4 chunks, right? And that's what we're going towards. Now imagine you take every single house that we spoke about earlier and we represent them as dots on this two-dimensional plane. You have a bunch of dots that get thrown up on this grid. And I'll admit, this is not realistic data. This is just data that we've put on there as an example to demonstrate patterns within data itself. And for anyone looking at this, right, you see that solid black line going at an angle across the board. You will see that this is representative of most of the data points it looks like, except for these few ones that lie far away from that line. And as human beings, again, as the slide suggests, we are heavily intuition oriented in being able to decipher these patterns in data when presented visually as represented in this two-dimensional grid. So let's talk about this entire chart over here. You will notice that there are 4 quadrants over here as we've laid them out. What we will try to talk about are the 4 quadrants in counterclockwise direction, starting from the lowest one that my mouse is over here. Let's call that quadrant 1. The one to its immediate right of screen is going to be quadrant 2. The one above quadrant 2 is going to be quadrant 3, so counterclockwise. And the one to the left of quadrant 3 is going to be quadrant 4. Immediately, without me prompting at all, a lot of you might decipher patterns right there. This might be something that you might do on a daily basis, and I apologize if it is, because we have to build ourselves up from simplistic examples. Let's do that. You will notice quadrant 1 is a really good quadrant if you're a buyer, because it's an okay quadrant, actually. Let me rephrase. It's relatively cheap. So these houses on the market, if I may throw a statement out there, are the cheapest ones on the market. Because there are quite a lot of houses that are more expensive than this one, but these tend to be on the lower end of the price line, which you see at the bottom over here. But they're also really small houses. So they're cheap and they're small, low price, low square footage. Let's look at quadrant 2. They're low price, yes, so they're cheap, but surprise, surprise, they're really big. They're high square footage. In fact, the house to the extreme right, I can throw a statement out there that house is the biggest house in the entire Singapore market if this slide represented all the houses in the Singapore market comprehensively, right? very few people will argue with that statement because it's visually accurate and you see it for what it is. Now, you're paying a low price but getting a big house. What gives, right? There's clearly something hidden in here, or there's clearly some missing information that you and I don't exactly see from first glance at this data itself, or this data representation, or maybe we're missing something. And that is actually a really good introduction into, let's not call them hidden variables, but attributes in their own right. Here is two-dimensional grid, X and Y, simply represents houses by square footage. But if we were to assume that square footage is the biggest indicator of a house's price, then this would be accurate. This would be entirely correct. And just given square footage, you'd be able to predict the price of a house. But clearly there are attributes outside of square footage, such as maybe the number of bedrooms a house has, or maybe location, like every single real estate agent will tell you, or maybe something like the age of the house. Newer houses tend to have more modern fittings and command a higher premium compared to older houses, and so on and so forth. So quadrant 2, while cheap, has hidden variables or additional information in there that we might be missing out on that are causing some sort of a skew in this data and giving us extremity, such as this really big house that's almost free, right, relative to the rest of the market. Quadrant 3 is self-explanatory again, and it's the opposite of the quadrant that the first quadrant that we saw, where it is really expensive, but it's also really big. And this kind of starts making sense, right? Where you can see the relationship over here being almost on a line or being linear, so to speak, where as the size of the house keeps increasing, the price of the house also keeps increasing. And there's an open question on chat. Is this the same material as last week? Only in the first few slides as we build towards complexity, and we'll do that over the next few slides. We'll actually be coding this out. In the previous module, we didn't. So hang in there for that. And finally, quadrant 4, where you have one house, which is super expensive, but really small. And for those who've been with us on the previous section or the previous run that we did at this topic, you will automatically notice that there are multiple explanations for these. One of which could be this house is basically the only open unit in maybe the Marina Bay Sands or some premium property like that, where it commands a premium for reasons other than square footage, which could be location, it could be fittings, it could be like a really premium or reputable property and all that good stuff. So without any of that context, if I were to just present this two-dimensional slide to you guys, a lot of people would very easily decipher that pattern represented on the red line over here, which is as the size of a house generally increases, typically the price of the house goes along with it. So bigger houses are more expensive, right? There are a few outliers to that statement, but they are what they are, outliers. But that just tells you that given a different representation of numbers, so there's not a single digit on this entire slide, and yet we're able to find some higher level intelligence out of this. So what that tells us is human beings are great at deciphering information presented visually in a graphical format that's represented visually, right? And given that you're able to represent or infer intelligence from graphical representations easily, you're also able to find out when it's a good deal or a bad deal. And you can see that circled over here. We've chatted about it a little bit. And you can see the outlier circled, which may or may not fit our generic broad-based stroke that we throw out, saying that prices increase as houses get bigger. Sometimes prices stay the same. If houses get bigger, sometimes they decrease. It could go both ways. Now, this is a fundamental principle of deciphering patterns in data, where, again, there are multiple methods, but one prominent method that we will be exploring in this topic, in this Zoom seminar, is going to be about how you represent data in different methods, graphically, spatially, geometrically, whatever, and then you get different patterns from those representations and thus decipher higher level intelligence within that data that could otherwise come across as being unordered, so to speak. Now, for all of you who have aced or still remember your high school geometry, you'll realize that the equation for a line that we see over here is simply represented by that equation in bold that you see over there, where the line is represented by simply y equals mx plus c. And here we'll simplify it to simply represent y equals mx, and m being a mix of these variables that we'll call theta, which is a vector that has all of the weights for all of the parameters that we throw in. Each parameter is simply an attribute. So in this simplistic example, while we are looking at a simple attribute of x, which is square footage, y equals mx plus c, and we'll omit the c for simplicity's sake, y equals mx plus c represents the relationship of the x variable with the y variable, where y is a multiple of x, a weighted multiple of x, right? But if you have more than one x, which is you have not just square footage, but you also have number of bedrooms, number of bathrooms, I don't know, is it a duplex, is it not a duplex, things like that, then each of those attributes add their own different variant of x and thus have their own weights. And that line has multiple weights and multiple x's thrown in over there, right? So the feature vector of theta basically represents all of those. You don't need to understand too much of this, because what we'll do is we'll demonstrate this using code. Now, very quickly, if we were able to learn or predict the equation of this line, if all of these dots were close enough to the line, then what we have learned is in this simple equation, we are representing the entire Singapore real estate market in a single expression, right? And that is, again, the fundamental principle of learning patterns within large clumps of data by representing them differently, where you represent them in one form, and then you learn an approximation to the data. Remember, you're not learning every single data point in there at all. In fact, you're just learning the equation of that line, which more or less represents all of the points, give or take a few, which are the outliers. And the accuracy of your model here depends on just how accurate you can be, or how accurate your data is as represented in this form to that curve or that line that you have learned. And you might be asking yourself, sure, I can learn the equation of the line, but how do I do that, right? One way is you can actually open up a plotting tool, and then you can give different equations or different weights to your x and see what happens. So for example, let's say m is 4 and x is x, right? So y equals 4x represents a line that looks like this. Okay, now let's say we don't want y equals 4x. Let's say we want y equals 5x. What does that do? You can see the angle of the line changed ever so slightly, and it's gone a little bit more vertical. Let's do y equals 0.5x and see what happens. You can see that this is now a straight line that passes through 0.5. Similarly, I can do y equals, let's say, 2x plus 0.5. And you can see that this line passes through 0.5 and is angled away and behind the 0, right? So behind the origin. So this is trial and error. This is simple, dumb, brute force. And for the question on the Q&A, I'm using Grapher, which is simply an inbuilt macOS utility. You can just command space Grapher, and that should open that up for you. Or you can use any graphing software. You can literally use Google Slides if you want. And go to a slide and just play with the line and see, if you can change the equation of the line to fit the points in your graph. That's all we're doing intuitively. But intuitively, what we're trying to do over there is use a brute force method to learn the equation of a line that best fits or comes close to best fitting all of the points in your data set, right? That's all it is. You can choose to do it this way, but this is stupid, right? What if you have 1 million points? What if you have 1 billion points? What are you going to do? That's not going to scale. So luckily, in statistics, there's a way to learn an equation of a line, and it's you learn it in parts. There are inbuilt ways to do it, which we will express in code in just the next couple of slides. But in essence, what we will be doing is we will be taking a transpose of a vector, multiplying it with itself here, x transpose times x, and then taking the inverse of that, multiplying it again with the transpose of x, and then multiplying it with y, which is the vector of target values, right? So x is your variables for one set of attributes, y is your target values. This assumes that you know what the points y and x are, and then you will simply be throwing these out into an equation that gives you the value of theta, or in our simplified case, the value of n, that minimizes the error, which we'll talk about in a bit, that minimizes the error that is generated by approximating these lines to your points, or this line to your points, right? So once again, it's not rocket science, it's super simple. We're trying to just learn the equation of this line. We can do that through a brute force method, but luckily in math, there's a formula that helps us learn the value of n that minimizes the so-called error, which is the difference between where the line is and where all the points are. And that equation is given here. So now for everyone on the call who is eager to hop right into code, let's do this. We will try to learn the equation of a line on random points. And we'll do that in 2 or 3 separate methods, and we'll see how that fits together, right? So I have a Google Colab open over here. Don't worry, I have a bit.ly for this, which is much smaller. I'm gonna just type this answer in and drop it in. I don't think chat is open for this one. Let me see if it, oh, there is chat. Here you go, to all. So I'm sending the bit.ly link and also the Google Colab link in case the bit.ly link does not work over in your chat. You should be able to see it. Let me know when once you're able to open it. I have run this code already to make sure that we don't have Murphy's Law playing out over here and we don't have anything breaking. And for the person asking, what did you miss in the first 20 minutes? If you already know linear regression, nothing at all. Just linear regression, at least an intuitive sense of linear regression. Okay, we'll give everybody a few minutes to just drop this in to your browsers. Hopefully you have it open. Let's say 20 seconds. Yes, good point. We will be zooming in. All right, so you can choose to read the code on the shared Zoom screen, or you can choose to open the browser window yourself. All the code is in there. This is a publicly accessible notebook, so feel free to go ahead and copy it yourselves or just get the code. It's literally got, I think, 3 or 4 code blocks, not much in there. And we just step through the code. Again, you don't need to have any background in Python or mathematics, apart from just having a sense of curiosity. If you do, that's great. If you don't, try following along. We'll try to keep it as open and accessible as possible, right? So let's step through the code and see what's happening line by line. In a Python notebook, the Google Colab that you have open and shared with you is basically an environment which has a bunch of stuff. Okay, so for the person asking, how do you copy, download, just file, just make a copy, you just save a copy in Drive, and you should be able to save it to your own Drive, your Google Drive. So answer live, sweet. So a Python notebook is simply a collection of, it's an environment that has a bunch of stuff previously installed on it, and it's a collection in there. What you can do with the Python notebook is you can run arbitrary code, that's usually Python code, and you can execute them in a browser-based environment that's a little bit more friendly, and you can save that so you can serve, you can send it over to your research peers and they can give you feedback in real time rather than having to compile a bunch of code on your own computer. People prefer that sometimes, people prefer this sometimes. So it's just a standard in the data science community that you use a Python notebook when you're doing some sort of collaborative research. So that's why it's called Google Colab, short for collaboratory of code. Now let's step through this code line by line, right? All we're doing in the first two is we're importing specific packages. Now, a package is just a collection of code. So some smart person somewhere wrote a bunch of code that abstracts away the complexity of doing things like simple calculus or doing things like complex calculus or something like that. And they're available in libraries all over the place. Some smart person also wrote out some code that does some plotting for us. Pre-run code is shown over here. So we'll be trying to do plots like this. And to do plots like this, you need to pull in the pyplot library from matplotlib. These are not the only packages that do this clearly, because a lot of people have different approaches to doing things. And you can do your own research in finding out other packages that do similar behavior. But in here, we're only getting a numerical computation package called NumPy. And we are going to refer to NumPy instead of these 5 letters as NUMPY. We'll simply call it NP. Changing this means you change your code. Wherever NumPy is referred, you want to change it to whatever you change this to. So if you want to import NumPy as N instead of NP, wherever NP is there, you just need to change it to N. Get it? Cool. So similarly, we're importing the pyplot subpackage from the matplotlib main package as PLT. As simple as that. Now, what we'll do is, if you recollect our problem over here, we want to first generate these points, and then we want to learn a line that approximates itself to these points. So first, let's generate the points, which is the X, right? All the X's, all the square footage. So we want first a random collection of points between 1 and 100, and we'll just pull them in using this command that I highlighted over here from the NumPy library. So it's np.random.rand 100, 1, and then we'll just simply multiply them by 2, right? Just to get them in a linear way, so to speak. Now, what we'll do is we'll also generate Y's, where we take whatever we have in X. So this is the mx plus c, right? So we take 3 times X, add 4 to it, and add a random variable at the end between 100 and a 1. And all we do from there is we just plot X against Y. Once that is done, we display the plot using a plot.show command, and you get this shown up over here. Yeah. Cool. Once you do this, you can either do Shift Enter, Command Enter, and first the Google Colab will hook itself up to a server, and it should execute the code for you. Once that initializing thing on the top right gets initialized, connected, now it's running it, it's importing NumPy, it's done everything, it's re-rendered that graph, even though nothing has changed for you guys. If you just copy pasted this code into a new code block, what has happened is it's simply just gotten all of these things, and it's run them line by line as we've gone through them. For the person asking what the B dot is, I'll simply state that what you're seeing on the plot are dots, right? So look up the matplotlib.pyplot plot method in library, like just search for matplotlib.pyplot.plot and look for the things that it accepts as parameters, and you'll see what the difference between B dot or like whatever else is. So you'll see that these are blue dots. That's a hint. I'll leave it as an exercise for the user to understand what the other parameters you can pass are to have different things rendered over here. So answer live. Cool. So what we have over here is a random collection of points. To illustrate that they are random or they're dynamic, nothing is truly random in this context at least. To illustrate that they change, just run your same code again by clicking your cursor into the same code block. Make sure you're in here, either hit play or Shift Enter, Command Enter, whatever. You can see that every time you do that, the points change, right? This is, this is intended because we are using a random function over here, which generates different points every time you run it, right? So this ensures that we have some sort of reproducibility, but like you will get different variations once we run this code. All right. So let's go to the next section. Now we have X's and we have Y's. We have a bunch of plots. We have a bunch of points plotted, and let's see what we can do with them. We're going to use that formula that we saw in our slide deck, where we want to calculate the value of theta or m that minimizes the errors that generates this line that approximate the line to all of the points in this space, right? As simple as that. So we just want to find the line that is closest to all of the points, not too far away. The way we do that, again, remember, is there's this mathematical formula. It is what it is. It is math. We'll try to first do this, and then we'll see if we can do this through the brute force method or any other method that we can think of. So this is called the normal equation, and the normal equation is rendered here on the slide, and it's also shown over here in Python using NumPy. It's literally exactly the same thing. We're getting the transpose of the XB matrix, which we create using another formula over here by passing X to it and then creating a vector or an array or a matrix, depending on how you see it, of ones between 1 and 100. And then we do that entire formula where we transpose a matrix. Let me just highlight it from inside out. We take that matrix we just created, transpose it, dot product it with itself, inverse the whole thing. So inverse of the whole thing from inside out, and then dot product it again with the transpose, and then dot product it with y. Right? So it's exactly this formula that you see over here expressed in NumPy code. You don't have to worry yourself with the math too much. If for the curious amongst yourselves, you can go and check out the normal equation and check out the proofs for the normal equation. I'm almost certain to bet that if you sat through high school algebra, or geometry, you've seen this. So, and you don't need to, but if you are interested, for the curious, you can go check it out. Here, once we do this, what we will get are two things, the M and the C. As simple as that. Every time you run it, remember, every time you run this block and this block alone, it should give you the same values. But if you change your dots up here by simply running the first block again, it will re-render your plots. So the line has to change, and thus running the normal equation again will give you a different set of weights that now generate a new line. And you can see the weights that we've gotten are 3.9 and 2.9, right? So y equals 3.9x plus 2.9 is, or so to speak, is the equation that we've gotten through this. Now, scikit-learn, which is a Python package, also has its own inbuilt way of finding a line that fits all these points. It may or may not be a more efficient way of doing it. So we'll try this, which is a different approach of doing what we've just done using the normal equation by using an off-the-shelf package, and we'll see what that does, right? So very simply, the way this happens is you only import the linear regression method from the sklearn.linear model package, just as we have for NumPy and Matplotlib at the top. And then you assign an object to a variable. So you're initializing the linear regression function by naming it lin_reg. And we call the fit method on X and Y that we already have up here. So X and Y that we created. All we're doing is fitting this linear regression method to X and Y. And you can pass the intercept and the coefficient from that simply by calling intercept and coefficient. And then if I run this for our versions of X and Y, this is a different method of computing the exact same coefficients that we saw previously, but through a different package. And you can see both of them are exactly the same. So we've arrived at calculating the coefficients for linear regression through two different methods, right? So you have the code shared with you. The brute force way of doing this is a method called gradient descent. And it is almost exactly what it sounds like, where we did this thing in the Grapher tool where we're creating multiple lines. We were looking at y equals 2x plus 5. Now we can do y equals 3x plus 5 or 0.5, or we can do y equals 3.2x plus 0.5 and so on and so forth. And you can slowly move the line up and down depending on where you want it to go, depending on how your points are laid out, and fit that line exactly for those points. Now, a way of doing that in math is using this principle of gradient descent, where you randomly throw a line up, and this is a high-level intuitive way of thinking about it. You randomly throw a point up on screen or the graph or whatever, and then you compute what is known as an error. The error for the line is simply the root mean square error. A lot to unpack over there, so let's go step by step. So the error in and of itself is for each point that you see over here in green, how far is that point from the line? You know from high school math that you can compute the distance between 2 points in a two-dimensional plane as a certain equation, x2 minus x1, y2 minus y1, you know that equation, right? So there's x coordinates, y coordinates that you subtract and you find a relationship between. So the error in the root mean square error is simply the distance between your approximation, which is the line, and the actual point on the property and price graph or whatever graph that you have. We take the square of that error. Why do we take the square? Because you and I both know squaring anything removes the negatives in most cases, unless you're talking about imaginary numbers or something, right? So if you square -2, it's +4. You square -1, it's +1. So you take the square of the errors first, and then you take the mean of all the errors, which is simply the average, and then you take the square root of the mean of the squared errors. It's just a lot to unpack. It's a little convoluted, but you guys understand it's not rocket science. It's simply layering complexity. Start with the error, take the square of the error, take the average or the mean of the error, and then take the square root of that mean square error. And that is root mean square error. You can see why we're doing each of these steps. We're taking the square to remove negatives. We're taking the mean square error to add everything and find the average squared error between everything, so that you're trying to find the best fit for all points and not just for 1 or 2 points. And then you're taking the square root of that for reasons we'll come across later. Sweet. Now, that's what you do. Another way of getting errors would be to simply look at the mean absolute error. And here it's the exact same way of layering complexity. You first calculate the error, and then you calculate the absolute value of that error instead of taking squares, because squaring does things that are sometimes desirable, sometimes not so desirable. Because if you square 0.5, what happens, right? So if you do, let's open up, what? Yeah, 0.5 times 0.5, you get a value of 0.25. Now, anyone who knows math knows that 0.25 is lesser than 0.5. Huh, interesting. But what happens if you do 5 times 5? You get a value much bigger than 5, 25 in fact. So squaring big things makes them really big, but squaring small things makes them really tiny. So if you want to lay emphasis on biggers, you would use square. But if you want to just use absolutes, mean absolute error is a good way to go. So there are pros and cons of doing both. I'm just quickly running through them. Using these measures of error, mathematically, you can do the equivalent of what you see on screen, which is you can start with something like y equals x over here in the left-hand corner. And then you can fit it to a y equals 2x, which is move the line a little bit more towards the vertical. And you can do y equals 3x or 3x plus 2 or 3x plus 1 and keep playing around with those equations until you're happy with the fit that your line gets. But to do this mathematically, you would have to express the error, which is where the line is and where all the points are on the plane, and then try to minimize that error mathematically in an iterative fashion. And that is a principle of gradient descent, where I'm sorry for the detailed math itself, but we take partial derivatives at every point when we essentially or whole derivatives depending on like the kind of gradient descent you're doing, to estimate which direction you need to move. So if you take an error, that error could be positive, it could be negative. So you want to minimize the error, which means if you start with a large variation of a large value for the error, you want to go to a point where the error is really small. So you can see this is theta on the x and errors or cost on the y. So if you want to minimize error, you want to go in the direction where the error is becoming smaller and smaller. And we'll keep this high level because this is a 101. But taking a derivative at a point tells you the derivative, tells you the direction you need to go. Tells you if you make a small incremental change to this value here, what will be the result and which direction that result needs to go into. You can derive from there. So we take the partial derivative across all directions and we head out in the direction where the error starts getting minimized. And that's exactly what we do. Every single step, we throw a line out there initially, random line. We look at all the weights. We try to look at which direction we need to move to minimize the cost, and we move in the direction. We do the same thing again. If we can minimize the error, we keep going down that path and we keep doing that iteratively. Now, the way this is expressed in code is in a final block in our Google Colab. And here, there are a few variables that you want to be aware of that we'll just touch upon on the surface, but you can learn about later if you simply want to search for it online. And the reason for that being at a high level, if you principally understand how all of these computations are done, then you can understand the details depending on which library you're implementing them in, or if you're writing them from scratch, as we are in this case. First, we express a learning rate, in this case, 0.1. We'll see how we use this. We express a number of iterations because we want to stop at some point and we don't want to keep going down a rabbit hole, so to speak, literally a rabbit hole. We express a value of m called 100. And then we express a value of theta, which is a randomly initialized theta value. Remember, we want to minimize this theta value, which is the so-called m value in a simplistic example of y equals mx plus c. And then we do a loop, which is for iteration in range of iterations. So literally loop 10,000 times, compute the gradients as so, and then estimate the new value of theta with the present value of theta in this loop minus the learning rate times the gradients. So the learning rate is simply a multiplying factor that determines how big of a step you take. And the iterations step through your code that many number of times. Doing this now, in one click, your algorithm has gone through 10,000 times and computed the value of these arrays, 3.9 and 2.9, which is luckily close enough to what we've gotten up here in this one shot itself. Alternatively, let's change the number of iterations to simply 10. And run that. So you can see that the value here learned is different. This is because this this code has not had the amount of iterative chances to come close to the level of intelligence that we've seen up here by approximating down to 3.9 and 2.9, which is the actual weights that we are looking for. Let's do 100. Closer, but not quite. 1,000. Close. So about 1,000 seems to be good, but after 1,000, if I go to 10,000 or even 100,000, it seems to be staying the same. So you can imagine what's going on in this version of almost force fitting your line to these points, or force fitting your curve to these points, wherein for each of these iterations, we're stepping through. If your learning rate is very small, then you'll need a large number of iterations to reach the point where your error is minimal, right? Common sense. But if your learning rate is too large, what ends up happening is your entire code or your entire steps start looking like this. Let's actually demonstrate this. Let's put the learning rate at something stupidly high, like 2.5. Not a number. Let's do 0.9. Not a number. Let's do 0.2. All right. So even 0.2 is stupidly large, it looks like. 0.3. Okay, that works. Okay, let's lower the iterations and then increase the learning rate. So you can see with a learning rate of 0.3 in simply 10 iterations, we kind of come close to our desired outcome. But if with a learning rate of 0.1, 10 iterations, yeah, it's a bit more far away, or it should be theoretically. But you get the idea. Small learning rates take a long time to come to minimum, but large learning rates can hop all over the place and give you those not a number values because you're just hopping around and like not actually doing too much productive stuff, and it's swinging wildly, so to speak. So that in essence might have seemed super simple, but what we've covered are a few really profound points. We first looked at representation of data in different formats, and then learning patterns within those representations. Really important for statistical mathematical modeling, where we are not looking at numbers anymore. We're looking at representations of information as points on a two-dimensional plot. And we're learning patterns or intelligence about those points from these representations in their own right? So it's simply data representation, forming the fundamental basis for being able to learn patterns from so seemingly unordered sets of data, putting order to them first. We also learned that human beings are great at deciphering or intuitively deciphering patterns within the data, and mathematically being able to decipher these patterns by using statistical methods can be as simple as learning the equation to a curve. That curve can even be a straight line. That straight line can simply be expressed as y equals mx plus c, where all you're trying to do is minimize the value of m or theta that represents that line in its own right. There are, we also learned that there are mathematically sound equations that help you learn equations of these lines in some points, and you can choose to use them. If it's a straight line, it's a normal equation. But if it's not a straight line, or if it's any line that you don't understand the normal equation or you don't remember off the top of your head, you can use brute force. And you can run the gradient descent algorithm to just throw a random line out there and cycle through moving that random line around, as we did in Grapher, multiple times, and get the equation just right by adjusting your learning rate and by adjusting the amount of iterations that you do. Cool. So there's one question on the chat about like, what kind of models will we be learning today? We'll be going through pretty much a whole spiel now. We started off with linear regression just to give you a sense of these fundamental topics, but we'll go through a lot more. So ETA in the code is actually learning rate. It's simply the multiplying factor for how big of a step you want to take. Is there a way? This is a very good question. Is there a way to compute learning rate instead of trying different values? That is an excellent question, and that's the kind of question that data scientists are paid a big amount of money to find out. The answer is it depends on the type of data that you have. So it's a lot of trial and error sometimes, but also educated guesses. And there are statistical ways to find out like good learning rates and everything. But it depends. How do we decide which one to use, mean absolute error or mean squared error? Remember, there are pros and cons to use either. Absolute are absolute. Squared makes big things very big and small things very small. So if you want to do that, if you want extreme emphasis on your big errors, then you use squared. If you simply want errors represented as errors, you use mean absolutes. Once you employ them in practice, you will see the difference between both the approaches. So I would encourage you to actually try them in a practice approach. I think there's a couple of questions that go along that same path. So, okay, in the interest of time, we'll move on. But you guys have the Google Collaboratory shared with you right now. And I cannot emphasize how profound the topics you just covered here are. We've seen 3 different approaches of finding the same answer, one using built from scratch methods, using gradient descent, the other using a prepackaged model or a prepackaged function imported from the scikit-learn library. And the first one being using the normal equation, which is the mathematical equation. So all three of those approaches amazingly gave us the same line, which means we're doing something right, which means that there's more than one way to solve any problem over here, right? Here it would give us the same line if we did at least 1,000. Yeah. So you guys now have that code, you can play around with it. Feel free to change out the randomness or play around with the different functions if you're familiar with Python. If not, it's a good introduction to start learning Python and all the libraries in there. Now, with that out of the way, we'll hop into our next module, and we just talk about a few things that are really important for data scientists to understand and to wrap your heads around. The first being this concept of dimensionality and talking about dimensionality reduction. We are fortunate thus far, and I'll just wait maybe 15 seconds to see if there's any other questions out there. What's the point of modeling if there are errors, however small? If there are no errors, what are you going off on? You're going off on guesses, right? So that's worse. So you want to minimize errors. It's never going to be perfect. You're right. You actually are nailing a very good, important topic, which is you're always going to get an approximation to the data. So always validate and challenge those things. Why are there two values in the NP array? Which NP array? This one. There are two values because one is a 10, which is the intercept. The other one is the coefficient. So it's y equals mx plus c. We're getting that mx plus c here. Cool. Q&A. Again. Another excellent question is, if there are already pre-built models for linear regression, why do we write our own model? Well, it might be a case where the pre-built model isn't good enough, or you might want to understand the fundamentals of the entire modeling process from scratch, or you want to implement your own way of doing this in a way that's catered to your hardware, your architecture. So many different ways. So customization most likely is why you would write your own thing. Are people in the industry expected to know the low-level details of each machine learning model, or is it more of the norm for them to just use libraries to do the work for them? Well, if you understand what the libraries are doing, you'll be able to call out the BS when it does happen. So for instance, if someone is using a linear regression model for data that you know is not linear, let's say it isn't like growing linearly, but it's got a weird relationship, then almost certainly you would not want to use a linear regression model. And that is when, if someone is doing that, you would call it out. So if you understand the low-level workings of the library, you'll be able to fit that properly. Can you show how to get the gradient descent formula? Yes, it's on the collaborative that's been shared. Check the chat. And we'll just hop into the next one in the interest of time. Now, we are fortunate thus far to be able to work with such really simplistic examples, right? Really looking at price as a function of square footage. How easy is that? You'll notice that most of your friends in real estate, or if you don't have friends in real estate, maybe you're not friends in real estate, you're brokers or whatever, are experts in being able to determine the price of a house given multiple variables. So square footage, location, number of bathrooms, number of bedrooms, does it have a terrace, does it have a pool, a bunch of things that even I can't throw out right now or imagine, but probably you can, or they can. How do they do that? There's so many attributes. What do you give a variable to, and what do you give a weight to, right? That's the question that comes up almost every single time in terms of dimensionality. So all you want to do right now is take a step back and imagine the room you're in. And yes, this is going to be a little bit hippie, but it's important to do this. Think of the wall in front of you and imagine trying to find, with your eyes closed, a random point on that wall. You can split the wall up into grids of 10 by 10. So if it's a 10-foot wall, each foot is a delimiter up, and each foot is a delimiter across. So if you were to close your eyes and one of your friends were to randomly put a point on the wall, there are 10 times 10 squares on that entire wall. So there's 1 in 100 chance, so to speak, that you will be able to identify that point on the wall, right? So this is just a two-dimensional wall. it's simply X and Y, like our example. But even there, your chance of finding one point amongst all the noise is super low. It's super low relative to what you would expect, right? You would not always get it right. Now, let's imagine instead of just a wall, you're imagining your entire room, which is a collection of walls in cubed space. So you have not just one wall, but you have that wall times the volume of your room. So there's not just length and width anymore, there's length, width, and depth. That is the equivalent of adding a third dimension to a two-dimensional space. So here we're speaking about dimensions as spatial dimensions. Spatial as in physical dimensions you can touch, feel, see, experience. Adding just that third dimension, right? Your chances of finding, let's say, a fly that's flying across your room go from 1 in 100 to 1 in 100 times the thickness of the wall times the depth of your room. So it increases many-fold. It's not just a simple increase in like adding another wall. You can imagine that the volume is much, much, much more than a simple wall. And that in and of itself extends itself not just to physical dimensions, but theoretical mathematical dimensions. Every attribute you add in adds another dimension to your data. And every attribute you add in thus adds complexity. So you can see in 2 dimensions, it's simply a wall. In 1 dimension, it's simply one line. In 3 dimensions, it's a cube. And in 4, it's a cube within a cube or a tesseract for all of you interstellar fans out there, right? So it starts getting really, really complex once you go beyond the 3 spatial dimensions that we live in. For example, if you want to really have your mind blown, just imagine a 3-dimensional building, right? If you wanted to add a 4th dimension to that, let's just consider time, not as a spatial dimension, but as a temporal dimension. And think about every single person, bird, dinosaur, what have you, that has inhabited that space that the building currently sits in from the beginning of like the Earth's existence until now. That adds so much complexity to your data in its own right, right? Instead of just thinking about the people who are inhabiting your room at this point, you're thinking about everything that has ever been, like millions, I don't know, maybe a billion years or something of evolution until now. So that's what it is. That adding each dimension adds a lot of complexity, and that's the TLDR, which is adding spatial dimensions or adding dimensions in your mathematical data adds complexity to being able to visualize or find patterns in the data in its own right. This is simply an illustration of the same thing. If you have points on a 10 by 10 wall, you have X amount of chance of finding one point given your eyes are closed. Now, if you add a cube and those points are spread out in the entire room, your chances go down significantly, not normally, significantly. And you might be asking yourself, will I ever use this? And the answer is, you already are in many, many, many different ways. In image representation, for example, if you're able to find amongst all of the dimensions, and this is a simple, let's say 40 pixels tall by 40 pixels wide pixel image of a digit. So in handwriting recognition and all that, if you're able to only pick the pixels that you know are likely to have a digit in it versus the pixels that do not, then you already have a strategic advantage because you don't need to process dimensions or pixels that you don't have data in. You can approximate all the data within this entire image in, let's say, just the area that my mouse is going over roughly, right? So you can imagine this area that my mouse is now going over, the edge, the corner, I'll actually do us all a favor and just draw circles. So this area, this one, and this one, and perhaps the ones between them on the edges, likely don't have a lot of information regardless of the digit you use. So this is the representation of 4, as you can see. But if I were representing a 1 or a 5 or a 6 or a 7 or any digit between 0 and 9, I would not imagine a lot of information to be stored in those pixels towards the corners, right? So those are additional pixels that I would have to process if I were processing this image. And if I were not to process those pixels, then lesser computation for me, lesser number of dimensions. That's the whole principle behind wanting to reduce the number of dimensions in your data. And that is why we want to do things like dimensionality reduction. Dimensionality reduction is both a statistical learning method, depending on how you use it, as well as an aid. It's an aid because it helps you reduce the complexity of your representation problem and helps you narrow down the scope of what you want to do in terms of learning patterns from your data, right? So imagine instead of having square footage, pool, no pool, duplex, no duplex, number of bathrooms, number of bedrooms, and all of those other added criteria. Let's imagine 10,000 different things that represent a house. If we knew that the top 4 criteria are simply location, square footage, number of bedrooms, and proximity to MRT or something like that. If those 4 things capture 90% of the house or 95% of the house's value, wouldn't that be better to simply model on compared to modeling on 10,000 different variables? Of course it would, if you're constrained by complexity or computation. Sure, I will slow down. Thank you for that feedback. So that is the principle of dimensionality reduction and why we would want to embark on doing dimensionality reduction. Again, this is a representation of the same image that we saw in the previous slide by only stripping out the pixels blurred in this image here that have information about the digit and representing in deep white all of the pixels that do not have information, which is pretty much the majority of the image. A small minority has the 4 in it. And if these pixels are active or have black in them, and everything else has white in them or gray in them, we can say that this digit is a 4 with a simple if-else condition as well. Now, we'll talk about this in a little bit when we're talking about trees, but the plot here and the citation below, that book is really good by Aurélien Guérin from O'Reilly. It's really good to understand the principles of machine learning because this plot is one of many plots in the book. It shows the output of a random forest model that ranks features, or in this case, pixels, based on importance. When confronted with a problem that has a large number of dimensions, this is one way to extract the dimensions of importance. Clearly, in image recognition, you would want to find the pixels of your image that best represent the problem you're trying to solve. For handwriting recognition, for example, that hotspot has all of the information, and those black spots have nothing. So you would want to only pick the hotspot because that vastly reduces the amount of pixels that you will be processing. One way to reduce dimensionality is through projection. Now, because this is a 2-dimensional screen and we are aiming to represent a 3-dimensional plot over there, you can see that all those blue and black points are supposed to be an ellipsoid thing in 3-dimensional space that's like curved on a plane. It's represented that way. You'll have to use a little bit of imagination to imagine that. So you can see that all of those points now, we've upped our game. We've shifted gears. Until now, we were talking about price and square footage. We're simply adding, let's imagine price and square footage was X1 and X2. We're adding an X3. Layer 3 has entered the game, which has another dimension that until now we weren't bothering ourselves with. And simply by doing that, you can see how complex this whole thing has become. While in our previous example of looking at price and square footage, you could very easily look at a line that's going to the top and going to the right. Here, you can kind of see an ellipsoid, but you can see it's a lot more complex. It's not as simple as our previous example, right? But one thing that's absolutely clear is that all of our training instances or plots lie on a 2-dimensional plane that's at an angle in 3-dimensional space, right? So if you were looking at this purely from a perspective that we are at present, it's angled. But if you were only to look at this from a certain angle, either above or from the right, you would look at all of these points in a different perspective compared to looking at it here, right? So we can say that within this higher dimensional 3-dimensional space, all of our training data sets lie on a lower dimensional 2-dimensional space. That is a very profound statement. Take some time to process that. That simply means that all of the information in these 3 attributes is in a subset dimension within the higher dimensional 3-dimensional space, right? that principle carries over into multiple dimensions as well. When you have thousands, tens of thousands of dimensions, it usually is the case because adding another dimension, if you were to spatially visualize it, adds volume, and thus adding a lot of volume is just not dumb, but it's large and unwieldy. If you could find a subset space, then it's very clearly going to reduce the amount of complexity in your problem, right? I'm guessing most on this call would agree with that statement. Now, if you were to visualize this plane, represented by those two axes that you see over there, instead of x1, x2, x3, let's call them z1 and z2. And we'll be looking at z1 and z2 from a top view. So looking down on the plane, you will see that we have reduced the dataset's dimensionality from 3 dimensions to 2 dimensions while losing almost nothing in terms of information from that higher level, higher dimensional dataset, right? Hopefully everyone agrees with that. If not, please drop a question in there. This is a little bit of a profound topic, but it's actually super simple. Once again, the summary is that if you have points in your dataset that are represented by multiple attributes or dimensions, there stands a chance that the bulk of the information within your dataset is not contained within all attributes, but the bulk is contained within a subset of all of your attributes. That bulk could vary between, I don't know, 99% to maybe 10%, but it's not always equally distributed across all dimensions, is the theory that you would want to exploit. So how do we do this, right? Or what are we doing over here? We're essentially projecting. We are learning, instead of a line now, we are learning a plane, the equation for this plane, or we're trying to find those two attributes within that, those two sub-attributes within that higher dimensional space that have all or most of the information in that higher dimensional space. Another way of, if you are really unlucky, is your dataset might not be so friendly, where it's simply an ellipsoid that can be put on a plane and can be projected down. This is a classic, and I mean figure 8.4, which you see over here. This is a classic dataset called the Swiss roll dataset. It's, I think it's a bakery thing, like a croissant or something, which is a dataset that's rolled in and of itself. So if you were to project this down into lower dimensional space, what do you get? If you look at the top view, you get a mixture of all of those points. And very helpfully, these points are represented as colored values so that you can see what happens when you look at the top view, side view, and so on. So when you look at the top view, it's spread out and everything is mixed together, almost like jelly or whatever. So you're not gaining information. The structure in the dataset is more complex. And this is just a simple illustration. Datasets in higher dimensional space can be, very exotically structured that you might not get full benefits out of, reducing dimensions. But what you would want to do instead of projecting is you would want to unroll the dataset. And this is another method of dimensionality reduction, which has mathematical methods in terms of like getting these. And here, once again, we're just illustrating by example, just unrolling and squashing side by side what the differences are, where if you unroll, as you see on the right, it's better for splitting out all of the classes, whereas if you simply squash them down, then it's not. One method of dimensionality reduction through a mathematical process is through this model or through this method of using something called the principal components analysis by doing singular value decomposition on your data. Big words, yes, but there's a simple mathematical equation, just like the normal equation that you studied in the recent past in the slides, that help you get a matrix of weights or a matrix of dimensions and basically tell you the amount of variance or information within each of those dimensions. So imagine you had 3 or in this case 2 dimensions as the image shows, x1 and x2, and you can see that most of the information on this plot is contained in a subdimension. Now we're looking at 2 dimensions. So a subdimension of 2 is 1, right? So most of the information in this plot is contained on that one line. And there are 3 possibilities of inferring lines. There are those 2 dotted lines. So there's one dotted line here, there's one dashed line, and a solid line. So clearly you, me, everyone on this call will automatically say that the solid line has the most amount of variance in there because it's evident from visual inspection. But the dashed line, this one where my mouse is on, that one has a little bit more variance than the dotted line, but not as much as the solid line. This is an example of, maybe iteratively looking at different projections that give you different amount of variance, and thus pulling out the ones that have the most amount of information that you want. And that is done through this method called singular value decomposition. For methods like this, I would highly recommend just using the inbuilt library functions that you have and not doing it from scratch, even though you can, but most scientific libraries have this inbuilt, and you can just do it from scratch by using the library methods from there. There's also measures of success that these library methods give you, including things called the explained variance, or the amount of variance that is contained in a subset of the dimensions. So one way to visualize them is to plot that measure of success called the explained variance across the number of dimensions. So here we have an extreme scenario, which is actually commonplace in industry, where we have 400 dimensions representing something. And you can see the explained variance as a measure of the number of dimensions. What does this tell us? Let's take it step by step. The scale on the Y is between 0 and 1. It can be read as percentages. So you can see that 80% of all of the variance or information in this data set is represented by less than the first 50. Let's say the first 50, right? So 50 divided by 400 is 12.5%. So this is a classic Occupy Wall Street slogan, where 12.5% of all the dimensions have 80+% of all of the information. So if you could reduce your problem down by over 86%, would you not? Just to get the same amount of accuracy that you would by training and increasing your complexity? Of course you would. So this is a really good way of using the explained variance as a function of the dimensions to estimate how many dimensions you want to reduce down to. Now, the obvious question we always get in scenarios like this is, how do I pick when I want to stop? It depends on your problem statement. So if you're dealing with something that is loose, like user visitations on your site, and you want to predict the number of users who are visiting your site, you're afforded a higher degree of error over there, then by all means, reduce down the dimensions as much as you can, if that speeds up your computation and thus helps you get the information out quicker. But if you're dealing with something like, let's say, insurance, or something that is like that has a bigger consequence, where if you have errors, then those errors can be really expensive or costly, then please try to have more information rather than less in mission critical applications such as those. So again, it's subjective. That's what data scientists are paid the big bucks for. Sometimes it's iterative, sometimes it's mathematical, sometimes it's based on experience. But I'd be lying to you if I said there's only one way to do this. There's almost always not. And it is a subjective field where you hop in, you take not a gut look, but an educated guess based on all of this information that you have learned about how this works. So understanding it from the fundamentals helps you make these choices in an educated fashion. So there's a few questions out here. We'll quickly address them and then move on to the next. How are we sure that it doesn't lose much data and convert it from 3D to 2D? That is what we use principal components analysis, and that's what we use the explained variance for. Look both of those terms up. I'll leave it as an exercise to you, but principally, if you understand what PCA and dimensionality reduction do, along with explained variance, then you get that. Now, will you be able to approximately simplify the dimensionality of a given data set all the way down to a 2D space, regardless of how complex it is in the beginning? Again, explained variance. If the explained variance says yes, like 2 dimensions contain 90% of all the information, you're doing a good job. There's always going to be loss. You're trying to weight the loss out against your gains. So it's a cost benefit analysis. Now, how do we determine how we project down to lower dimensions, which dimensions are important. PCA gives you the outcome of those dimensions in like literally importance ranked fashion. So all that is taken care of for you. The library method for PCA is very self-explanatory. If you've written any code in Python, you should be able to take a look at that, read it, and implement it very easily. And I'll leave it as an exercise to you, purely because this is a 101, and we don't go into that much level of detail at this point. Will there be ready-made functions in Python to do this enrolling of the plane? Yes, that is exactly the scikit-learn method for PCA. I'll leave it as an exercise to the readers to do that. Singular value decomposition is one method of getting dimensionality reduction. There are others. SVD is used primarily in combination with principal component analysis, and you can use that over there. Now, there's a few more. I'll leave this as an exercise to you guys, like where you learn PCA. It's simply statistics, right? It's like, where do you learn cosine? Yeah, you can just Google it, I guess. If you understand the principle behind what we're doing it, I'll leave you with a cool application in industry that will help you get your brain wheels turning and help you think about different ways of using it. Imagine you're the owner of a website, right? And you have, I don't know, 10,000 different metrics that you're tracking. Everything from page load speed to user visits to user history of purchases or clicks or any of those things. Let's imagine you have 10,000 of these, right? And you want to know the most important attributes that define a user or something. Isn't PCA something that you might consider using over there in terms of high value actions that a user might take? Yes, that is actually exactly what that is meant for. You're trying to look at the most important metrics or features that all of these metrics contain as a subset of themselves. And that is one way of doing it. We saw another early on, where if you're doing image analysis, you can find the pixels that have the most information in them, and so on and so forth. So I'll leave it as an exercise to you. It's simply statistics. The applied science portion of it is where people make the big money, which is if you can think of a different way to use this to solve a problem that's not been thought about solving in this way in the past, then ka-ching, or it's a good exercise to do. And we'll move on in the interest of time, just because I think we want to cover at least one more type of model, which is decision trees. But I just want to pause right there and tell you how far you've come already, right? This is a ML Models 101 course. We don't want to simply go through the academic exercise box checking of just telling you this is a model, this is a model. That's not what we're here to do. We're helping you to build up intuition from first principles. So far, let's take a look at what we've seen. We've seen something that looked super simple, from representing data in a graphical method and thus deciphering patterns from there. But I will submit to you that this is one of the most, actually, this is a really good way of imagining how statistical learning works, which is you have information that could be ordered in one way or not ordered at all. You take it and you represent it in a different way. It could be in a two-dimensional plot, as you're seeing over here, or it could be in a completely different way, where you have pixels in an image, or you can take those pixels and put them up in an array, which is linear, which human beings might not be very intuitive with, but machines are. And then you decipher patterns within that now differently ordered set of data using mathematical methods, statistical methods, or just common sense and brute force, which is the gradient descent model that we saw. And by doing any of these, you're able to approximate curves, could be a straight line, could be a curved line, could be whatever line, to data. You're also able to approximate not just curves, but you're also able to approximate inferences such as these are my important dimensions from PCA and extract that value from there. So you've learned some really cool fundamental topics that will hopefully inspire you to learn a little bit more about them. I'm sorry we're not going into too much detail on any of these. It's meant as a 101. If you're interested, please reach out to us on LinkedIn or on just drop us a note, I guess, over email, and we might be happy to engage. We can't share these materials with you, but hopefully you're taking notes. That will hop right into decision trees. All right, so decision trees. Let me see if I can share. another slide. I might have a bit more color into this. Yeah, that's that. So a classic machine learning problem is being able to look at these things over here, which are flowers of the iris family or the iris species. So there are 3 flowers here in this so-called iris species dataset. The first one is the Virginica flower. The second one is the versicolor flower. And the third one is Setosa flower. Now, I'm sure if a lot of you are in the data science field, you would have seen this multiple times, but for those who haven't, if you just take a look at these flowers, and even for those of you who have, if you take a look at these flowers, if you just eyeball them, you see that all 3 of them look different, right? They clearly have some differences. One of them seems to be this drooping little guy over here with Setosa. Another one is a little bit more pale. Let's not look at the color. Let's just look at the length and width of the petal and the length and width of the sepal, which is, surprise, surprise, what the dataset contains. It basically has the name of the flower. It has the length and the width of the petal and the length and the width of the sepal. And using just those 4 attributes, the theory is we should be able to separate out all of these flowers into their families or into their individual subspecies of the main iris. Can we do that? And this is a classic machine learning problem, which multiple algorithms are tested against. One such algorithm is this algorithm called a decision tree. And we'll talk about what a decision tree is right now. Throughout all of these examples that we were throwing out so far, we made a logical leap that we're using intuition, we're using some mathematical method to decipher an approximation to the data. But a lot of you might just be thinking, why do we do that? Why don't we just use if-else statements? Why don't we just say if house in Newton, in our property example, if house in Newton, if house has 2 bedrooms, if house greater than X square feet, then price equals X. And then write those if statements, else statements, then statements like 200 times, 2,000 times, 2 million times. Won't that suffice for everything? Well, in a way, you're right, which is that is kind of how human experience is built. Pardon me. Excuse me, pardon me. But in a way, it's really hard to generate all those if-else statements. What if you make an error? How are you going to compensate for that? It's really hard. A decision tree is a way to learn those rule-based outcomes from your data itself. And interesting, okay. And these rule-based outcomes can be learned simply by feeding the data in to a decision tree algorithm and having the tree greedily split. So the tree is just as it sounds. It is a collection of nodes where decisions are made and splits or branches where they branch out. So each branch is branched based on one decision, and each node is where the decision gets made. So let's just take a look at this tree without having any other context about decision trees and understand what it's doing, right? So we're looking here at the white top of the tree, which is the root node. Here, we take, remember those 4 attributes, petal length, petal width, sepal length, and sepal width. We simply look at the petal length, nothing else. So this reads like if only the first line, if petal length in centimeters is less than or equal to 2.45, then if it's true, don't look at anything else. We split to the left. If it's false, we split to the right. As simple as that, right? So with this one statement, we're able to split all of class Setosa, and we'll see how. Gini is a measure of impurity. So we can compute Gini, we'll look at the formula in a little bit, as a mix of the classes. The whole point of a decision tree is to split in a way that Gini is minimized for class-based split. So for example, if you're trying to find a cat or a dog, that's where you'd use a measure of impurity for splitting them in that way. You can also use them to predict if a price of a house is going to be 250 or 280. That is a continuous variable. And we'll talk about that in the next bunch of slides. But here, the whole objective is trying to minimize this measure of impurity. And what is impurity over here? You will notice that we have 150 samples starting off. So there are 150 mixed flowers, of which there are 50 versicolors, 50 virginicas, and 50 setosas. If you remember the three, I don't blame you if you don't, those three flower families: virginica, versicolor, and setosa. Simple as that. All we're doing over here is the decision tree algorithm tries to find the value of any of these metrics that it's been fed in such a way that by picking that value or that line, the rest of the data set is split into a way where Gini is minimized in one format. So here, if petal length less than 2.45 is true, then Gini becomes 0, and we get all setosas bumped into this left segment, and we don't need to split anymore. Here, Gini's gone from 0.6 to 0.5, so yay, we're winning, but not quite. We still want to minimize Gini further, or depends if you want to or not. That's subjective, and that's what we put forth when we are writing out the decision tree algorithm, which is just like we set out number of iterations for a gradient descent algorithm. Here, we're putting out, we might choose to put out how much Gini we want to minimize down to, or how many nodes we want to, or how many splits we want to make. Here, we still have 100 samples, because remember, 50 samples of setosa have been taken away. And we have 100 samples split between versicolor and virginica. And because we have an equal 50-50 split, it makes sense that Gini is 0.5 or 50%. Here, Gini is 0.667, higher impurity, because there's 1/3 of each class in there. Here, the decision tree algorithm seems to split at petal width less than equals 1.75. And when it does that, the right-hand node has a lower Gini value, where there are 46 instances of the virginica class, and the left hand has 49 variants of the versicolor class. So this is predominantly versicolor, this is predominantly virginica, but there is some confusion. One thing that is versicolor is still being classified or still being interpreted in RFL's logic as virginica, and so on. Similarly, 5 things that are virginica are being interpreted as versicolor, and that's the mix. That's what Gini is telling us, which is here, there's a bit of impurity. It's about 0.168. That's because there's some mix. So you might want to split further if you want, but it's no big deal. It's just 0.168. You live. And that's exactly what the decision tree algorithm tries to do, which is we start off with a root node, and then we basically just keep splitting in and splitting in and splitting in with the objective of minimizing Gini. Now we've stopped here, but there's no rule that we stop here. The decision tree algorithm is flexible. You can choose to set your own Gini and keep splitting should you choose to. And for those on the call who have just joined and you want to follow along, I've cited the book that we're using as instruction material over here, Hands-on Machine Learning with Scikit-learn, Keras, and TensorFlow Concepts, Tools and Techniques to Build Intelligent Systems, or Leon Geron. It's a really good book. I recommend it. Alternatively, you can just go to Scikit-learn K-means or something, and Scikit-learn is really good. They have a really good set of documentation in the user guide for all of these things. So if you're interested in reading, you'll find a lot more than what I'm throwing out here if you're of a scientific bent and you just want to read it. But that book is like very beginner friendly if you want to buy it. It's good. Cool. So we've seen this again, but the amount of splitting that you do expands the depth of the tree, so to speak. And the samples are simply samples. It's the number of total training instances mixed together at that node. The value is the number of instances in each class as an array of segments in that node. And then Gini is the measure of impurity. Another way to think about this is to imagine the spatial boundaries. Now, again, we're going to represent the data in spatial form. simply by taking, and this is, I don't know why the image is messed up, but let's try to reduce it. Nope. Anyway, so we take petal length on the X and we take petal length on the petal width on the Y. And you can see petal length is 1, 2, 3, 4, 5, 6, so on. But hey, do you remember our tree? In our tree, we split at petal length less than equals 2.45. So all we're doing is we're drawing a straight line at 2.45, and that's depth equals 0. So this is again a way of representing data by using just these two attributes. We can use any other two. This is just an illustration, so please don't worry about that. At depth equals 1, which is this dashed line, you remember we did petal width equals, what is it? Less than 0.175. 1.5 is here, so 1.75, I trust is somewhere there. So it is less than 0.1.75, which is all of these things. No, it's these things. Yeah, it is these things. It's the blues. And that is what it is for depth equals 1. Now, for depth equals 2, because array started 0, it's depth equals 0, 1, 2. At 2, we're doing petal length again. This is just a shade under 5. It's not illustrated here, but you can choose to split it. You can choose to split if you were at just a shade under 5. And here you can see the so-called confusion, the confusion that we illustrated in this depth between the green and the purples over here. Where there are 5 purples in the greens, as illustrated here. And there should be 1 green mixed in with a purple, as illustrated here. Or yeah, you get the idea. But that is an illustration of how, if you have enough if-else statements, like literally lines saying, if this is this, cut it, this is this, cut this. You're splitting your data set in a way intelligently where you can find pretty good rules-based logic learned from your data itself by some measure of success or failure. Now, the way the decision tree algorithm works is through this thing called the classification and regression tree algorithm, or CART. There are really good write-ups for CART all over the internet. Again, it is what it is. It's standard statistics. So it's very easy to apply this from the standard libraries itself. You don't have to go and rewrite this from scratch unless you're doing it as an academic exercise. Most library packages also have the added goodness of working really well with the hardware accelerated libraries at the hardware level, like the Intel MKL libraries for your Intel CPU cores if you're running it on a CPU, or similarly for NVIDIA's CUDA and all that if you're doing neural nets and all that. So I would just trust those libraries for these basic things, or even for the more advanced things for sure. So here you can see that for feature A, what the CART algorithm tries to do is it picks some threshold T of A, and it tries to minimize Gini for simply feature A. It tries to minimize Gini for feature B. It tries to minimize Gini for feature C and feature D. So for each of these features, which could be petal length, petal width, sepal length, and sepal width, it picks thresholds, keeps moving them around, and tries to find a good threshold for which it splits the data set accordingly. Now, depending on that iteration, depending on that node in the tree, depending on what wins out over here, that threshold is picked and set. And that's how, in the first instance, for example, the CART algorithm decides that petal length less than 2.45 is a really good measure of reducing the impurities at the next level of splits, and so on and so forth. Now, similarly, a decision tree again, until now, we were making classifications on like cat or dog, or versicolor, virginica, or setosa. But it can also be used to figure out, like I said, if a value or a price of something is like 320 or 310 or 280 numerical values, right? Continuous variables that can have multiple variables in there. And before we look at how, it should be very obvious how actually, let's look at the representation so that you can form your imagination of what's happening with the decision tree itself. So Please ignore the red lines. Just focus on the blue dots, similar to the blue dots in our random example for the linear regression model. You can see that this is a curve. It's a U-shaped curve between X and Y, where X ranges between 0 and 1, and Y also ranges between, looks like minus negative 0.2 and 1.0. So it seems really hard, right? How do you estimate a value? This could be all house prices in Singapore. They could start off really high with one attribute and then keep declining and then increase again. How do you learn a curve that fits this? You and I can both see that the best curve to fit this would be U, right? It would be something that is curved, that looks like that. You can't really do it with straight lines, or can you? Well, for anyone who's done computer graphics, you'll know that a circle is simply a collection of very, very, very small lines stitched together such that it's imperceptible to the human eye. So with enough depth, yes, you can. But that is also a good and bad thing at the same time. And let's talk about that from a common sense perspective. If you were to do just this, where you're learning Y from X, and you're splitting X at 0.197 here, and splitting it at 0.197, has this minimizing effect on this other measure of success called mean square error, which we encountered in the past. Mean square error is reduced from 0.098 to 0.38 here, 0.038, and 0.074 here. And there are further splits on X at each of these depths, which give us different reductions in mean square error. In a common sense way, all of this is math. You don't need to worry too much about the math. It's very common sense what's happening. It's essentially this. For each depth, we're essentially plotting a straight line. And then we're splitting that data set into two. And you will notice that different depths have different splits of the data set, not necessarily uniform. So you can see at depth 0, the solid black line that is thrown out over here, the data set is split into two, everything on the right and everything on the left. You can see everything on the right is more voluminous compared to everything on the left, clearly, right? Because there is more apparent variance in the left side compared to the right side, or vice versa, whatever. You can see that there are points that require fewer lines to plot in the left-hand side of the depth 0 split compared to the right-hand side. Again, you don't need to concern yourself too much with the math unless you're interested, but all we're doing over here is splitting the dataset multiple times. You can see here, we've added max step 2, so you only split it twice. Here we're splitting it twice. And the red lines that we've learned are closer approximations to the curve. You can imagine if we keep going down this path and keep splitting with max depth increased significantly every single time, you can go from 3 max step to no restrictions at all. And in this case, our red lines go wild because the tree keeps splitting, and it goes to a point where each point has its own split. So you have that scenario where it's like 2,000, 20,000 if-else statements. But you can also choose to restrict the growth of trees by restricting the number of samples that are allowed to be split on. And if the sample number falls below that, you don't split it on. Where you don't want to approximate to one point, you want at least 10 samples in a node before you split, right? So instead of adding a depth parameter, you can add a minimum samples leaf parameter. And there are multiple such parameters that you can think of, where you can also add a Gini parameter, minimum Gini. You can add, or mean square error, whatever it is that you're trying to minimize, or you can add any other things that you want to stop or have fulfill a condition before you split, so that you stop the growth of the tree beyond a point. I'll pause right there. I think there's a question about, is it important for classes in the dataset that a decision tree is trained on to be uniform, aka similar quantities of data points for the different classes? How would the data not being uniform affect accuracy of the model? Very good question. I believe this was asked before we encountered decision trees approximating curves to data that looks like this. Clearly, each split does not split the data in a uniform way by your measure of uniformity, but you can still split it. So you're approximating the curve regardless of that. Decision trees are actually one of the most undersold types of models out there, because they're not exotic models that require like calculus to run, but they're really, really powerful. So in cases where you're doing anomaly detection, or you have multiple features that might be spiking, and there are anomalies on billion row scale data or whatever. I found random forest to be like really, really good in putting forth a very strong response in near immediate amount of time. But the downside of random forest is you'll need to have some sort of labeled data to reach that. You can also learn the trees automatically, but like having labeled data will give you, or having some measure of like how you bias the model to learn is going to be better, clearly, because if you don't know what those flowers are, you need to segment them in some way before you use the random forest model. So yep, it is what it is. We won't be sharing slides, but you can take screenshots. I can't stop you there. And all the citations are below. So you can buy the book if you want to. It's a really good book. Sorry, I'm hoping not selling them too much. Now, let's cover ensembles. Before, I think we have 15 minutes to go. So we just cover ensembles and we'll try to do k-means clustering if possible. You already come so far, right? In this short amount of time, again, I know I'm beating a dead horse. You've seen linear regression, and the representation of data in different formats to give you different informed perspectives, or the ability to learn different layers of information from that lower level data. We've seen gradient descent, which is a fundamental building block of all things neural network, the new hotness in the data science community over the past few years. We've also seen the expression of errors when you're approximating curves to data. We've seen root mean square errors and what they mean. You've seen mean absolute errors, and given another type of error, you should be able to reverse engineer them because it's not complicated. It's simply the error with some mathematical operation on top of it, like square root or squares themselves, or taking an absolute function off. We've also seen dimensionality reduction, which is a fairly advanced topic, but it's actually super simple, right? You understand adding dimensions adds volume and thus complexity, and reducing dimensions is usually a good thing if your data is weighted in a way where most of the information is contained in a subset of the space, because that helps you with complexity of computation. Finally, we've seen decision trees, and we will now be seeing ensemble methods. An ensemble is simply a fancy word of saying collection, right? So imagine you have multiple classifiers, right? Multiple types of classifiers. In the data science community, it is usually a good practice if you're starting off with a small amount of data, or if you have a sampled set of data from a larger data set, to run multiple variations of models to see which one best fits your model. If it's easy for you to do, and you're just doing an exploratory run compared to knowing and having researched your data into like what exactly it's doing, and then going after it that way. And you could have a scenario where each of these models might be good in their own right, but all of them may or may not be able to be used together. And you have to make a choice to pick one, or do you? You don't actually need to do that. An ensemble simply refers to a voting amongst a collection of classifiers. Ensemble models are simply that. The type of voting, the mechanism of the vote differs, which results in different decisions different times. But every time a new instance comes in, you don't just pick one model and put all your eggs in one basket. This is basically spreading your risk. Another way to combine, and I'm just reading off the slide over here because it's simply, it's very straightforward. Another way to combine model output is to consider splitting a dataset into multiple random samples and training the same type of model on all of them. And later taking a vote amongst all the classifiers, that results in a stronger model overall. This is called bagging or bootstrap aggregations, if the sampling is done with replacement. It's called pasting otherwise if it's done without replacement. Now, what does this mean? This is a little bit convoluted, so let's just take a second or so to understand this. Imagine you walk into a new job, you're working at an e-commerce company or something, and the e-commerce company's data science team comes up to you, they're like, hey, good job, intern, on passing your interview. Now, here's this massive data set from the past 5 years, go do your magic. And you suddenly have like billions of rows, 5 years of data with so much in there And you can choose to train one model on 5 years of data with all the variance in the middle, all the seasonal and cyclical effects, everything that goes on inside. Or you can choose to train that same model type, could be a logistic model, it could be SVM, it could be any other model type, on uh, random samples of that entire data set. And do multiple random samples and thus multiple variations of your models, and then take a vote amongst all of them. That way, if there's any subset of data, or if the entire data set itself tends to average out noise or average out patterns or whatever, then you're spreading your risk out in a way where you're letting that bagging or pasting approximation that you're doing, or that splitting that you're doing, spread that risk out for you. So this is the same model type on multiple splits of the data itself, as opposed to another way wherein you have multiple models trained on the same type of data, all taking a vote. The mechanism for the vote is what makes the ensemble method tick. Finally, another way, a way to think about this is you can bag multiple trees together to reduce the irregularity of the decision boundaries. So here, for instance, instead of simply having decision trees like we saw that split on tep, or whatever, you can have a decision tree trained on one set of data and have multiple trees and have all of those trees vote, which gives you a forest of trees, so to speak. And the image over here basically represents what I just said, which is on the left-hand side, you have a decision tree, but on the right-hand side, you have 500 decision trees with bagging, which is we are sampling the data, and then we are replacing those samples and then sampling them again. And then we're training 500 trees on that principle, on that type of data. And then we're aggregating all of them together, and we're taking a popularity vote or like all that good stuff. That gives us the curve on the right-hand side. So decision trees with bagging, really good. It seems to approximate the data in a more intelligent way compared to this random haphazard way of straight lines cutting over, and it looks like some really badly drawn state geography lines or something, right? So decision trees with bagging, one of the most powerful types of models that I personally come across that are not neural networks. You can actually also boost them, where you sequentially train an ensemble of trees, with each iteration adding another tree that does better on the misclassified items on the previous trees. Sequentially training with adding trees that do better every single time is called boosting. When a new tree is made to fit only on the residuals, that is only on the things that were not fully classified by the previous tree, this is called gradient boosted trees. And you would have heard these in the past, which is gradient boosted decision trees or GBDTs. And you can see over here an illustration of such a sequence of steps, where we have a training set depicted in blue, and we have H1 of X1 represented in green, and we have the ensemble predictions for H of X1 is H1 of X1. So in this case, we're simply getting H of X1, which is the hypothesis function for X1 in this case, and we're plotting it as is. Now, we basically take out only the residuals, which are only the things that you see over here that do not fit the curve closely. And we put another hypothesis function, which is H2 of X1, which is this little bit of a capped curve that you see over here. And you can see this, our original hypothesis function, the one here in green or red, depending on what you see at the first level, is now modified to have this additional quirk in the curve that comes closer to predicting the data. Similarly, we only look at the residuals in whatever this second depth is, H of X1 equals H1 of X1 plus H2 of X2, H2 of X1. We look at the residuals here, and we notice that we can come up with a H3 of X1 that looks like this. And you can see finally we modify our residuals over here towards the top right that fit this final set of residuals. So by doing this in sequential fashion, we improve the results each time. And there are multiple methods in terms of which you can choose to stop. In BigQuery or in any other Python scientific library that has an implementation of the gradient boosted decision trees or similar ensemble models, there are different parameters that you can use to choose to stop. You can use early stop, you can pick the learning rate and the number of estimators, and you can do a lot of cool things that tune the trees that stop them at the right time. But this is not of as much consequence as simply understanding this slide, which is we start off with an initial hypothesis function and then we train additional hypothesis functions, thus trees, on simply the residuals of the data, and then approximate the curve as it comes closer and closer. I'll pause right there because I'm conscious of time. We're coming up just about on time. If there are any questions, we'll take them live. If not, okay, so there are a few questions. For bagging and pasting to work, do the classes need to be balanced? Good question. I think we'll follow up. If you could drop us a LinkedIn note, we'll follow up on that in a little bit more detail. There are classes where you would want them to be balanced. It depends on the kind of problem you're trying to solve. In most cases, the data is what it is. So you'll have to clean it up and normalize it and do all those things for before you start training the models themselves. So we can follow up with a specific problem you're trying to address here. So I think the question about what is an array, the first number is the intercept and the second number is the coefficient. That is correct. That's absolutely correct. You can read the documentation about the linear regression model in scikit-learn to learn more about that. The title of the book is the one that's shown here in, let me make it bold, the credits. So it's this one. Hands-on machine learning with scikit-learn, Keras and TensorFlow. Just search for the author name, Aurélien Cheron. Oh, really? And you should get that. There'll unfortunately not be any slides shared, but you can take screenshots or you can take notes. Good question. So won't combining trees make the tree less accurate? As you can see, clearly not. Combining trees makes the trees more accurate, not less, or more or better fitting to the data. You can see over here, a single tree is limited by the amount of approximations it can make. Decision trees with bagging, 500 of them, an ensemble of 500 of them, tend to do much better in terms of like smoother curves, approximating the data closer. So here you can see this is half as hard. This might be a reflection of overfitting, where small variances in the data in your sample, in your training data over here, tend to have oversized results, but here it's more smooth. Right? So it might be more closer to production data. Is CAT also able to predict which category a new data point will fit in? Yes, that's the entire point, which is you learn patterns in a training set and then you deploy it to a production set to learn those, infer those same patterns in unseen data. Would bagging also cause overfitting though? It's a chance, there's a chance, which is why we don't want a case that looks like it's not bagging technically, but you don't want a case like this. So you want to restrict your trees to reasonable boundaries. So yes, you're right. Okay. So a bunch of other questions about like the syntax and stuff. I think the code speaks for itself. The code is shared with you. So hopefully copy it because I'll be making that private. I don't want to keep a Python notebook exposed to the public for a long time. So maybe in a day or two, I'll just make it private. All right, so we have 2 minutes to go. I'm conscious of time. And thank you so much, guys, for coming to our session today. If you have any feedback, good or bad, please scan the QR code on screen right now and leave us some feedback. We'd love to hear from you. How do you vote on the predictions of all the trees in GBDT? Does each decision tree have a different weight on the vote? That's where the decision algorithm itself plays a part. I will leave it as an exercise to you. That's the mechanics of how the implementation is done. But it's a really good question, which is you don't really need to know the details of the math. Most of these are like black box models anyway. If you're just building them, you